Hello, everyone. My name is Hardy Hinton, and this is Group Table 1, Greens, Project 2. And we decided out of a list of problems to choose the second one on the list, which was problem 2 with the boxes. And so in this problem, we I decided to draw a diagram representing what it looked like, and we had a blue box, which is represented here, and we had a red box, which is represented here. I didn't have a red marker, unfortunately, otherwise I would have drew the red box in red. But otherwise, so to describe what we've got going on in this problem, there are two boxes, like I said, one with a mass MB, and so I decided to denote those over here too. So MB just simply is the mass of the blue box. MR is the mass of the red box. And so denoting that, then they are sitting, we know that these boxes are sitting on a level horizontal table that is frictionless. So that's one of the main assumptions that I decided to include up here is that there's no friction occurring on this table. And so we know that. And so then another important assumption is that the collision of the boxes is inelastic. And what that means is what's going to happen is this spring here is we know it's a known compressed distance. So this spring gets initially compressed, and so that's on this left half of the table. And so then the blue box slides to the right and then makes contact with the red box, and they stick together. Instead of bouncing off of off of one another, the two boxes stick to each other, and so then uh, they slide together both to the right, and then approach this unknown other compressed spring that we're going to be trying to figure out what its compressed distance is. And so um, we know that this spring here too is also an identical spring to this one, and they both must be ideal springs for this problem. And so our goal then here is for this whole entire problem to determine the maximum distance that the second spring compresses here from the first one initially making contact with it. And so then another assumption is that momentum is conserved. And so that leads me into where we got to describe the quantities that are in this problem. So there's something else important to note is that there's not any numbers involved in any of these solving situations. So we decided to denote every quantity with just letters and known masses and stuff like that. And so we know that U represents potential energy. I already described what MB and MR are. We know that K is the spring constant. And so that will be involved in how much these springs are compressed. And so then VI and VF are the initial and final velocities. And so those are going to be in step two's process of the solving. And so then PR and PB represent the momentum of the red box and the momentum of the blue box. And so those will also be found later on. And so then a couple of really important laws slash equations to include are U spring, which is going to be the momentum of the spring, which is a half kx squared. And so this, like I said earlier, has to be an ideal spring for this equation. And so then Ke is the kinetic energy, and that's a half mv squared. And so those are a few of the laws that we need to know for this problem. And so then assumptions, like I said, this table is frictionless. There's no friction occurring when these boxes slide across, and the collision between them is inelastic. And then also the momentum is conserved. Those are all our important assumptions and simplifications to make. So then to draw this physically, I decided to draw a momentum diagram. And so here it represents what's happening after the initial box moves across the table. So first, initially, the blue box moves a pretty good distance to come into contact with the red one. The red one doesn't move at all because they make contact with one another. Then the system moves the same distance total as what the initial blue box moved first. Then in our change column here, we see that the blue box loses some momentum as it makes contact with the red one. Then the red box moves to the right with the blue box. Then the system as a whole does not change because momentum there. Then in our final momentum, the blue box and the red box have to equal the same is what the final momentum arrow is here for the whole system. So we don't know necessarily what their exact masses are, but we know that they have to be relatively equal. So therefore, we can assume that these two arrows have to be the same in order to do this. Thank you.
Okay, I'm Toby, and I'm gonna go over the process of how we solve the second problem. We're gonna take this in steps. So we're gonna start with step one, which is finding the initial velocity of MB, or the blue box. And for this, we're gonna need the spring potential energy equation, which is U, which represents potential energy, S as a subscript to represent the spring, is equal to 1/2 K, which is the spring constant, times the Xi, which is the initial displacement, or how much MB compressed the springs, square. We're also going to need the kinetic energy equation, which is kinetic energy is equal to 1/2 mass of the blue box times the initial velocity squared. And for this, we're going to assume that uh, this interaction is elastic, and no energy, or sorry, not elastic, is conservation of energy, and the all of the potential energy is going to go into kinetic energy. So we can set these equal to each other and take away the halves, and then solve for VI. And for that, we get initial velocity is the square root of K times Xi, or the initial displacement, divided by the mass of the blue box. And that's step one. Step two, we're going to find the final velocity of the system, which we are categorizing as the blue box plus the red box. And that will be we're going to represent as mt later on. And for this, we're going to assume that the momentum, that this has a conservation of momentum when they collide. So for that, we can see the momentum of the red box plus the momentum of the blue box is equal to the final velocity times the mass of these two added. And this is why we needed the initial velocity, was to find the momentum of the blue box. And for that, if we plug that in and then solve for our final velocity, we get final velocity of the system is equal to square root of k x I squared divided by m over b times mb, or the mass of the blue blocks, divided by the total mass of the system. And that is it for step two. And then finally, for step three, this is where we find the final compression of the rightmost spring. And for that, we're going to assume that this is also a conservation of energy collision. So that means that the kinetic energy of the system when it hits the spring is all going to go into potential energy, and that is when the spring is compressed. So that for that, we're going to put the spring potential energy and kinetic energy system together, and we get m, the mass of the total, times v final squared equals 1/2 k, or spring constant, times xf squared. And we're trying to solve for fx, so we can cross out the halves because those will cancel, and then we'll solve for xf, and then plug in our final velocity equation that we got over there. And that gives us the final displacement for the rightmost spring is equal to the square root of mass total times square root of k x I squared over m mass total times the mass of the blue box squared over k. And then if we simplify that, we get the final displacement is equal to x initial, or the initial compression of the leftmost springs, times the square root of m, the blue ox mass, times the total mass of the system divided by the total mass of the system. Thank you.
Hi, my name is Ali, and I am from Group Green in Table 1. We decided to do the problem number 2, and this is the sense making of the problem number 2. Since the blue box is initially in contact to the spring and starts from rest, it will experience a restoring force. We had to calculate the velocity of the blue box at the time of collision with the red box. We had to analyze both the collisions and the collision of both the boxes and determine the maximum compression of the second spring. By doing that, we had to solve relevant equations to determine the maximum distance that the second spring compresses in response to the collision between the blue and the red box. For the units for the final and the initial, we decided to keep them as meters, while the mass of the boxes are in kilograms. By doing that, we can cut off, the kilograms and end up with this equation here, where we can also cut off the kilograms and end up with meters, which is what we wanted from the beginning. For a special case, if the mass of the blue box and the red box are equal, we can say that the initial is 0. This case only is assumed if if there is any perfect elastic conditions, which is, in the real world, like, it's likely to happen. Um, this problem was similar to one of our homework problems, which was in week 7. The difference between those two problems is that we had to, for this problem, we had to basically measure the distance of the spring and how it spreads, while the other problem we had to measure the distance of the two boxes. We also had this problem for recitation as well, but it wasn't that much similar as our homework in week 7. Thank you.